Let's take a look at notes 5.3. We're going to talk about exponential functions today. So, what is an exponential function? Well, I'm glad you asked, because that's what we're going to do today. Start off with what it looks like in the equation. It will be y equals some c, where that c is just a constant. Could be 1, could be -1, could be 7, could be a fraction of some sort, okay? But it's some constant, some real number. Okay? And then we'll have another number here, and that number is what's called the base. That value is going to be greater than 0. But to keep this as exponential, we're not going to use 1. So it could be between 0 and 1, 1/2, 1/3, 5/7. It could be greater than 1. Could be 100, could be 1,000, could be 1,000,000. Okay? And then this is what makes it exponential. You can see we've got a number out here, a number as the base, and it is exponential because our variable is the exponent. That makes this look like an exponent. Or excuse me, an exponential function. Sorry about that. And then the domain here is all real. We can use any number we want for this exponent. Okay. And then we do have some limitations on our range. And that range is based upon what our c value is. If c is greater than 0, then no matter what, our y value is going to be greater than 0. Okay, remember, a is going to be a positive number, so no matter what we do with our exponent, that exponent of a positive number is going to be a positive. So if c is a positive number, all we are going to get here are positive numbers out of it. Okay? And then, of course, if c is a negative number, it's less than 0, then there's no way that a to the x will change this back positive, and all of our values will be below 0. So let's write down some quick little examples so at least we have in mind what it might look like. It could look like y equals 3 to the x, where our c is 1, our a, the base, is 3. We could have y equals 5 times 2 to the x. c is 5, a is 2. Or it could get a little bit funky, and we could have a negative number out in front, and we could even have a fraction as the base, and a fraction that's less than 1. We could have a fraction that's greater than 1. And we might start seeing some that have a fraction for the coefficient, and we could even have in decimal form the base, and we might even run into cases where in the exponent there's an expression of x. So let's go back to a basic setup here, and you can see that we've got a y equals 3 times 2 to the x. We know that this is going to be exponential. And one way to help us with this graphing is to do a simple little t-table. The values I want to consider are -1, 0, and 1. Why do I like that? Well, first of all, let's look at when x equals 0. We know that 2 to the 0 power will not be 2, not be 0, it'll be 1. Anything to the 0 power is 1. So this will be a 1 times 3, and we'll get 3. So we know that this is going to go through 0, 3. That's going to be the y-intercept right here. The other easy one is to when when x is 1, that means this will be a 2 to the first power, or 2, times 3, which gives us 6. So we know it's going to go through 1, 6. Go to the right 1, and then we'll be up at 6. Now, be careful here. When we have a -1, this isn't going to make it a negative number. Okay? Think about what we see when we see a negative exponent. Okay? If I have something that looks like this, say a over b, and I take it to the negative exponent, this doesn't change a to a negative number or b to the negative number. Remember, this is really called a reciprocal. We take something to the negative first power, we do a reciprocal, which basically flips this. The a goes to the bottom, the b goes to the top. Okay. We flip it. So when I see this 2 to the negative first power, okay, I'm going to end up flipping that. Okay. We know 2 to the negative first power would be the same thing as 2 over 1 to the negative first power, and we flip that, and that becomes 1/2. So this is going to be a 1/2 times 3. We just multiply across the top, multiply across the bottom, and we get 3/2. So at -1, we'll be at 3/2. Woo-hoo! Yeah. So we can go to the left one, and we'll be up halfway between 1 and 2. Now, if we connect the dots here with this and extend it out, now you can see what a exponential function looks like when we graph it. And take a quick look at this. From here, you can see that our c value is 3. That is, of course, greater than 0. That's why all of this graph is above the y-axis. Remember what we said up here. When c is greater than 0, the range will always be y is greater than 0. Now, I also want to look at our a value. Our a value is 2. A equals 2. And a is greater than 1. That's pretty obvious. Remember, we said a had to be greater than 0, but it couldn't equal 1. It could be between 0 and 1. It could be between 1 and, theoretically, infinity. Okay? So, when we have this, when a is greater than 1, we will always end up with something that we call exponential growth. The graph is always going to be going up like this. Like a jet taking off, or a rocket taking off. Okay? It's coming out, going up, 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 like this. Exponential growth. All right, let's consider the next one. In our next one, it actually is the same graph, except instead of multiplying by 3, we're multiplying by -3. So let's think about what that'll look like. Our x and y, -1, 0, and 1. So instead of taking 1 and multiplying it by a +3, this will be a -3 times that. And then, of course, a -3 times the 2 when x is 1 will give us a -6. And you can see that everything we would have gotten in this graph is actually a negative number. So instead of going to +3 for the y-intercept, we're going to go to -3. To the right one, we'll have to go down 6. To the left one, we'll have to go down halfway between -1 and -2. And when we graph it, it's going to look like this. So the difference between each one of these is the fact that on this one, our C value ended up being less than 1, or excuse me, less than 0. -3 is less than 0, which means all of our values are going to be down here below the y-axis. Okay. When C is greater than 0, we're never going to go below the y-axis. When C is less than 0, we'll never go above the y-axis. Okay. Let's take a look at the next one. Okay. This time, our C value is 3. We're right back to where we were before with the C value of 3. It's going to be greater than 0. So if what we said is true here, we should expect that we're not going to drop below the y-axis. Everything will be up here. Okay. And let's think what this looks like this time. Okay. So we've got, again, -1, 0, and 1. When x is 0, well, that's still going to be anything to the 0 power 1. 1 times 3, so this is 3. So this also goes through 0, 3. It still has the same y-intercept as the other at y equals 3. When y equals 1, this will be a 1/2. 1/2 times 3 will give us 3/2. So we'll go to the right one and go halfway between 1 and 3 for our point. And then think about the -1. Remember how we said we flip? So this time we have 1/2 to the -1st power. When we do the reciprocal or flip this will be 2 over 1, or 2. And of course 2 times the 3 is going to give us 6. So we'll go to the left one and up 6. That means when we connect the dots here, it's going to look like this. And let's look closely here. This time our A value was 1/2. That is less than 1. It's between 0 and 1. When our A value is between 0 and 1, we're no longer growing. We're actually in a case of exponential decay. Okay. And briefly, let me just kind of point out to you why this is growth and this is decay. When we are growing, every time we increase that exponent by 1, we're multiplying this by 2. we're getting twice as big. We're at 6 here, we're going to get twice as big, go to 12. Twice as big, go to 24. So you can see how it jumps really fast. But this one is 1/2. Every time we increase x, we're half as big as we were. We were at 6, went to the right one, we're half of 6, we're at 3. We went to the right one, we're half as big, we're at 3/2. Then we'll be at 3/4. Then we'll be at 3/8. Okay? And you can see that fraction gets smaller and smaller. If we go the other way, it would have been before 6, we would have been up here at 12, because half of 12 is 6. Before that, we would have been at 24, 48, okay? 96. Okay? So exponential decay whenever we have that. Okay? So let's take a look here and see if we can figure out which one of these graphs matches this description. If we have a y equals c times a to the x as our function. So now, which one has the greatest c value? How am I going to determine that? Okay. Well, here's the easiest way to find our c values. Take each one of these curves, and we'll look at this one right here first. You'll see that it intercepts the y-axis, this axis right here. It intersects that at 0, comma, is that 5? Oops, I'm off by 1. 0, comma 5. That means when x equals 0, we got 5. When x equals 0, remember anything to the 0 power is 1. So that means this one, our c value has to be 5. When you look at the y-intercept for these of this form here, the y-intercept will always tell you what your c value is. So what's the c value of the function they call number 2? 3. It goes through the point 0, comma 3. So when x equals 0, we have 1 times c, so c is 3. And then, of course, what's the c value of the third one? Or, I'm sorry, the number 1 function. This is 0, 2, so our c is 2. So which one has the greatest c value? That one, obviously, is function number 3. Which one has the smallest c value? That one, obviously, is function, number 1. It goes through 0, 2, function 1. So, to repeat, when we're looking for the c values, all we have to do is compare the y-intercept. Okay. Now, a values. Let's compare our a values. Well, first of all, okay, you can see here is that y-axis. Okay. We know that each one of these c values is positive. It kept it up above that. But now the difference is between these is, take a look at how this one and this one, the red one and the green one, they are growing. The purple one is decreasing. So that is an easy giveaway that number 3 has to be the smallest, because this is the only one that has decay. And remember, with decay, like we noted up here, whatever that a value is, that has to be between 0 and 1. These two are both exponential growth. So, what do we need to do? Well, to look at our exponential growth, look at when x equals 1 and see how much we grew. We went from 2 here to, it looks like, probably 6 right there. In this one, we're at 1, 6. Okay. So we went from 2 to 6 by going to the right, so that's implying that our a value is 3. Remember what we said here? Since it's 2, it's twice as big. If the base were 3, then we'd be 3 times as big. Over here, we said we are 1/2 as big, so if we were, say, 1/3, we'd be even farther down here. Okay? So, again, in order to find our a values, what we're doing is comparing where we were at the y-intercept to x equals 1. And you can quickly see that if we looked at this one, when x equals 1 on this one, we're way up here. Okay? So what we're going to see quickly is that 2 has the greatest a value. And why? Because we're going to say that one grows the fastest, as opposed to the last one, which grew the least. It actually went down. Let's take another look at another set here. Okay. So again, one general thing that I can see here is I know all of the c values are greater than 1. Which one would have the greatest c value in this one? Anybody want to take a stab at that?
1.
Number 1. And what did you base that upon?
You can't see where it intersects the x-axis. Oh wait, is it the y-axis?
It is the y-axis that we're looking at. And yes, that one does have the highest value of the y-intercept, so we know that its c value is the largest. Which one would have the smallest c value then? 2. Find the y-intercept. That y-intercept's down here. It looks like it's at 1/2, doesn't it? Okay. So it's going up like this. So that one has the smallest c value. Okay. Now, which one's the easy one to find with our a value? The one with the greatest a value or the one with the smallest a value? Kenley, which one?
Which one is?
Yeah, which one? Yeah, if you were to decide, hey, I'm going to bet my last $100 that I'm right here, which would you choose to do? I'll bet that this graph has the greatest a, or this graph has the smallest a. Which one are you pretty certain of?
I think number 2 has the greatest a.
And why is that?
Because it's the only one that's going up.
Yes, this is the only one that has exponential growth. And exponential growth is based upon our a value. We know for sure that the a value here has to be greater than 1, as opposed to the other two. Both of these have exponential decay. Both of those are going down. Okay. So now we have to choose which one is smaller, the a value in 1 or the a value in graph number 3. What do you guys think? Which one has the smaller?
I said
3? Because it
intersects with the x, like x equals 1 the lowest.
yeah, you can kind of see it's going down faster. Okay, whereas this one, okay, it's decreasing, but not as much. So, for example, this one might be, say, 3/5. This one might be 1/5, something like that. So yes, this one decreases the fastest. Okay. Let's take a look at something called E. E is one of the most important math numbers that there are. It's actually called Euler's number. And yes, you'll hear people say Euler's number, but it is pronounced like Euler. And it is an irrational number. Remember, with irrational numbers, that they cannot be written as a fraction or a decimal that terminates or has a repeating pattern in it. This starts out with the value of 2.718. And why do I have you write that down? Because usually, if you recall from Algebra 2, that's all the set that we usually use when we're trying to memorize it or use it in our calculations. If you were to continue on, you would see it has all of these numbers, and no matter how hard you look, you'll never find a pattern in those. Okay. So, why is that important? Well, it's going to show up in some of our exponential calculations. We're just going to kind of pause that thought because it's going to come up down here. But before we do that, let's go ahead and do a little bit of solving here. Okay, so we'll kind of work through a little manipulation with our numbers to make the algebra nice and easy. Okay? So there's a little note here. It says both sides of the equation can be written with the same basis. Okay? So what we have to remember is this rule that power to a power, we would always multiply our exponents. I know you probably had your Algebra 2 teacher say this more than 100 times. Power to a power, multiply. Power to a power, multiply. Why is that important on this one? Because we want to get the same basis here. So first thing I'm going to look at is I have 4 here and 8 there. They're not the same. If they were the same, take a look down here below to our first practice one. We have a base of 3 and a base of 3. So if these are equal, if this truly is equal, don't both of the exponents have to be equal to each other? That makes this a simple problem to solve. All we have to do is say 4x minus 3 has to equal 5x minus 7. We jump from an Algebra 2 problem, a college algebra problem, right back to Algebra 1. Okay. Subtract 4x from both sides, add 7 to both sides, and what do we get? 4 equals x, or x equals 4, and we're done. But you'll see on the next two, we don't have the like bases. So let's go back up to our example here and say, what could we do to get like bases? Well, the first thing I can recognize is I know that 2 squared is 4. So rather than write 4, I could write this as 2 squared to the 2x minus 1. How does that help me? Well, I can also write 8 as 2 to the what? Third. 2 times 2 times 2. 2 to the third power. Then we use this power to a power property and multiply these. When we multiply those, we'll be left with an expression that has, or an equation that has an expression with 2 as the base here and 2 as the base there. Okay? So remember, When we multiply, we're going to distribute, so this will be a 2, and then 2 times 2x will give us 4x, and then 2 times negative 1 will be a negative 2, and on the other side, this will be just 2 to the 3 times x, or 3x power. And now we have one that looks like the first practice problem. It is an equation with both sides having like bases. Therefore, the exponents have to be equal to each other, and we can just take this 4x minus 2, set it equal to 3x, subtract 3x from both sides, add 2, and x equals 2, and we're done. Let's get like basis on the next one. Well, not a lot we can do here on this side. 5 is 5, but wait a second. Think about 125. Wouldn't that be 5 times 5, or 25 times 5? 5 quarters is $1.25. So this is 5 to the 3rd power. Don't have to do anything with the exponent here. Now we have like bases, 5 and 5. We're going to take both of these exponents and set them equal to each other, giving us 2x plus 1 equals 3. Subtract 1, divide by 2, and x equals 1. Our last example has a base of 9 and a base of 27. We know that 3 squared will give us 9, and 3 cubed will give us 27. We know that this is still raised to the negative x minus 2 power. This all is raised to the x. So these two are being multiplied together to give us those exponents, and that's going to leave us with the common base of 3. So it'll look like this. Power to a power multiplied. 2 times x is 2x. 2 times negative 2 is a negative 4. 3 times x is 3x, and that's what we set equal to each other. We say that 2x minus 4 equals 3x. We're going to subtract 2x from both sides. That'll give us x equals negative 4. All right, let's take a look at a particular problem here. It says between 9 p.m. and 10 p.m., if you arrive at Burger King's drive-thru, cars will be there at a rate of 12 cars per hour. The following formula can be used to determine the probability being P, that a car will arrive within t minutes of 9 p.m. So t equals 1, that would be 1 minute after 9, or 9:01. T equals 5, that would be 9:05. T equals 10, it would be 9:10. So first of all, it says, hey, let's make sure we understand how to do this. And that is, it says determine the probability that a car will arrive within 5 minutes of 9 p.m. So this is a case where t equals 5, and we're going to calculate P of 5, which would be just 1 minus e to the negative 0.2 times 5. Not sure I can do that very well in my head, knowing, of course, that e is this number that goes on forever and ever and ever. So we're just going to go to our calculator and let our calculator do this. And not only that, but let's put this in our y equals. so that we can, maybe we will, this doesn't want to, there we go.
Do you have a charger?
Do I have a charger? Yes. Let's go into our y equals. Clear. Clear. What type of connection do you have? This one. Nope. That one. There we go. All right, let's put that into our y equals, and our y1, we'll just go 1, and then minus, and then over here is that e, just to the left of 4, it's the natural log, the inverse of that, and then we'll put in a negative 0.2 and x.
Wait, how do you get the inverse of it?
So, in order to get the blue ones, or the, in your case, yellow ones, press the second yellow key, and then press the one with the natural log on it. There we go. Okay? Now, let's go zoom and 6. Remember, that's a negative 10 to positive 10. And it looks like this. And there's our graph. Okay? And remember with these, this one's nice because all we have to do is go to our table, second and graph, and in the table we can put in the value 5, press enter, and it's going to do the calculation for us and tell us that this will be 0.6321, and we can, since it's asking for probability, I'm going to change it to percent because people have a little bit better understanding of percents than decimals. The next one says determine the probability the car will arrive within 30 minutes. So this is the same problem, except instead of 5, we're doing the probability of 30. Oops, it's already entered in my calculator down here. So that gives us 0.9975 or 99.75%. Okay, so what's that saying? It's almost certain that between 9 and 9:30 you're going to get at least one car coming by. Okay, and it's going to be a very rare occasion, at least at this Burger King, that you're going to go for those 30 minutes and not see a car.
It doesn't look like that.
Okay, let's go back, and first of all, press zoom and 6. Okay, let's take another look at our equation. And okay, what we want to do is we want this to be our equation. So this is where we're going to put the x in here.
Oh, for the 5 in?
So yes, well that one just calculated this number here. It just gave you that. We want the equation to be in there so we can look at the graph of it. Okay. And that's what the graph is going to look like.
Oh, and then you went to table and
Then you go to the table And that's when you enter in those values in there.
Thank you.
Okay, well, you're welcome. All right, the next one says, at what time t is the probability of the car arriving going to be 50%? So this one is different. Remember, all of our function problems, we've tried to give you examples where it says, here's t, find p. This one, it's here's p, find t. What is t? P of t equals not 50%, because this calculation is going to give us in decimal form, or 0.5. And remember how we solve these types of problems? We go into our y equals and go down to y2 and put in 0.5. Then we're going to go up to second calc, and we're looking for the intersection of those, option number 5. I have the blue graph, that's our y1, reflected up here in the left corner. I'll say, yep, I want that one. It automatically jumps to the y2, the red one, our second curve. It's going to ask me to guess, and I'm not. And then the Frogger jumps to where they intersect. And that intersect gives us on here the x value, which of course we know is t. And that says that t equals 3.465. And remember, t is the amount of time in minutes from 9 p.m. So this is saying that you got a 50% chance of seeing a car within roughly 3.5 minutes. I think this is a pretty busy Burger King, right? Especially late at night. Maybe it's a Friday night and there's things going on, but yeah, you've got a 50% chance that you're going to see one car within 3.5 minutes of 9. Okay. Now, what happens to the probability as t gets larger and larger? Okay. So this is expanding our understanding a little bit. Let's take a look at this equation and try and answer it here. And we're not going to use our calculator on this. We're just going to kind of think this through. P of t equals 1 minus e to the negative 0.2t. Okay. So as this gets larger and larger, remember, if we are a negative exponent, this thing is going to be flipped. So I could write this as 1 over e to the 0.2t. Now think about this. Even though it's 0.2 times t, we know, say for example, if t equals 1, let me put t and then 0.2 times t. 1, we'll get 0.2. If we're 10, we're going to get 2. If we're 100, we're going to get 20. Now think about a really, 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 really big number here. Can you see where this is going to get bigger and bigger and bigger and bigger and bigger? That means we're going to take 1 and divide it by an even bigger and bigger number. So when t is 10, we're going to take 1 and divide it by 2, we're at 1/2. When t is 100, we're not going to be at 1/2, we're going to be at 1/20th. When t is at this really, 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 really big number, we'll be at 1/200 million. So how small is 1/200 millionth? If I put that in your bank account, would you jump for joy? If I put in 1/200 millionth of a dollar in there? Would you quit school and live off the money forever and ever? No, because what did I basically give you? Nothing. Okay? This, as t gets bigger and bigger, is going to go to 0. What's 1 minus 0? Do you need your calculator for that one? What's 1 minus 0?
0.
1 minus 0?
Oh, 1.
1. Guess what? As t gets bigger and bigger or goes to infinity, the probability of seeing a car is 1. And doesn't that kind of make sense at this real busy Burger King? That the farther you are away as from 9 o'clock, you're absolutely going to see a car. There's no doubt you're going to see a car. It's that busy. Okay? So, as t gets bigger and bigger, the probability of seeing a car is almost certain. Okay? All right, let's take a look here at a comparison over some of the things we've done so far. Okay? So, let's take a look at this. And it says, let's examine the two tables and decide, it says two tables, but I see three, if they are linear or exponential growth. And can you write a formula to describe the relationship between these? Okay? So, let's take a look at these and see what we have here. First thing I do notice is that in all of these, the x values are all just increasing by 1. So there isn't really any trickery that they're trying to do here. We go from -2 to -1 to 1, 2, and 3. So let's focus on the y values. When I have 7, if I go to 4, that's what? -3. When I go from 4 to 3, that's -1. And then all of a sudden, I'm adding 1, and then I'm adding 3. That's an interesting pattern here. Not sure what's going on there. Let me take a look at the next one. I don't see an addition here, but I do see a multiplication. I'm multiplying by 3. 1/3 times 3 is 1. 1 times 3 is 3. 3 times 3 is 9. So in each one of these, we are increasing by multiplying by 3. And then the final one over here looks like I'm adding 2, and still adding 2, and adding 2 for all of these. So first of all, which one of these, based upon what we see, is the linear one? Can you see that right away? What's your thought on the linear one?
It's
Number 3. Why is that?
because it's increasing by a constant rate.
Increasing at a constant rate. Isn't that what a linear function does? We know that if we have a linear function, linear functions, they always go up or down at a constant rate. That's called the slope, right? No matter where we go on the line, it has the same slope. Okay? So yes, this one's going to be linear. Oops. Easy for me to spell. And what would that function look like? Well, I do know right here is kind of a key number in this, right? We know the slope. Slope has to be 2, right? And we also have 0, 5. Isn't that our b value? Isn't this the y-intercept of 0, 5? So we can write this as y equals the slope, +2, times x, plus the b value, the y-intercept of 5. Linear functions are going to be increasing at a constant rate. Okay? Now, let's take a look at these, because I do want to point out to you that was linear. If we have something that is exponential, okay, an exponential is always going to be increasing or decreasing. It's going to go up or down. At an increasing or a decreasing rate. The slope is either going to get steeper or the slope is going to get less steep. Okay? Think about it. On an exponential growth, you can see how the slope is about 1 here, and then 2 here, and then it's all of a sudden 10, and then it goes to almost an undefined slope. And you can see on an exponential decay, I've got a negative 10, negative 2, negative 1, negative 1/2, and now it's going to 0. That slope is going to 0. So the slope is always changing in an exponential. So it will look like we're increasing, but again, it's increasing times 3, times 3, times 3, times 3, rather than addition. We also can see, since we have the value at 0, we know that our y-intercept is at 0, 1. That means our c value is 1 in this one, isn't it? This tells us that c equals 1. And our a value from our function, our general equation, is what this constant rate is. So this means that this one is our exponential, and it is y equals c equals 1 times a, which is 3, to the x power. And believe it or not, this one is neither exponential or linear because there is no constant rate in here. I just threw a parabola in here. This is parabolic. It's an x squared plus 3. Why do I know it's plus 3? Because you'll see it has the y-intercept of 0, 3. So it got shifted up 3. All right. So again, the big difference here that I wanted to point out was between these two, that linear, we always have that constant rate of change. As opposed to the exponential growth or decay. It's always going to have a increasing or decreasing rate of change. Yeah. And then if you remember back from Algebra 2, you ran into an exponential model that is applied to real life problems, and that was, remember the PERT, y equals p times e to the RT problems. Okay. I'm going to change it a little bit just because that's typically what's used in pre-calc, calculus, and college algebra is they just use c rather than p, and it's cert. It's the same function, but they just kind of do a switcheroo on you. Okay? So we have a deer population in Butler County. In 2000 it was 300. In 2005 we have 500. Assume an exponential growth rate. And then it also says a nice thing to give us cleaner numbers when we're talking about years is let t equals 0 be the year 2000. Okay? So that would mean that when t equals 1, we'd be at 2001, and so on. Okay? So based upon the information that they give us, we know at 2000, when t equals 0, we're at 300 deer. And then in the year 2005, when t equals 5, we're all the way up to 500 deer. So we want to write an equation based upon this. So we're going to substitute these numbers in. That is y, the population, is going to be 300. We don't know what c is. We don't know what our r is, but we do know that t is 0. Of course, r times 0 will be 0, e to the 0 will be 1, so right off the bat, we know that c has to equal 300. This actually is our y-intercept, our starting point. If we were to graph that. Okay. Next, let's substitute these values in. This will be 500 equals c times e. In this case, our t is 5, and this will be, oops, wait a second here. I know that c is 300. Let's not put c in there. Let's put what it is, 300. And this will be e to the r times 5. So if I divided both sides by 30, I would know that e times to the 5r would be 500 divided by 300, or 5/3. A little trick we learned with our solving back in Algebra 2 was to get an exponent out. We could take the natural log of both sides to get this out. So when I take the natural log of both sides of these, in other words, the natural log of e to the 5r would equal the natural log of 5/3. We had a rule that we can apply here, and that rule was if we take the natural log of some base a to the b power, that exponent, the power, can be written as a coefficient out in front of the natural log of a. You may not remember that, but we will use it now.
Wait, what's on the b times natural log of a?
Natural log of a. A is the base, b is the exponent. That would be the same thing as taking the exponent and putting out as a coefficient and multiplying it by just the natural log of a. If you put both of these in the calculator, they would give you the same amount. And that's nice because let's go back over here. That means this exponent, 5r, can be multiplied by the natural log of e, and that will equal the natural log of 5/3. And then another thing we might recall from Algebra 2, and that is that if you put the natural log of e in your calculator, you'll get exactly 1. This right here is 1. The natural log of e is 1. Which means, to solve for r, all we have to do is take the natural log of 5/3 and then divide that whole thing by 5. Put that in your calculator, you should get 0.102. And actually, I think I'm going to add a couple decimals on there because this equation can be sensitive to exponents. All right, let's take a look at the next part of the problem. Or I'm sorry. Yeah, it says write an equation for this. I think I've run out of room here. So I'll just write this down below here, what our equation is. The answer to this, our equation would be y equals the 300 for c, the e to the r value of 0.10216 times t. It says using your equation, what would you predict the population was back in 2010? This is a case of 2010 is when t equals 10. We need to calculate y of 10. 300 e to the 0.10216 times 10, which means I probably should pull my calculator back out and take a look at this one and see. So we'll go to our y equals, we'll clear out this guy, and while I'm at it, clear out the other guy, and then we'll type this in, 300, and then that same second and the natural log button, and we're going to raise this to the 0.10216 times x. And like we did the last time, I'm just going to jump over to my table and then enter in. Oh, 10's already entered in here. So I know that this is going to give us 833. And since it's 0.29 and we're talking about deer, I'm going to always round down because we don't have that next deer. We've got one little mama deer out there ready to give birth, but not yet. Yeah. And then it says, using your equation, how many deer you think there were in 1995. Ooh, wait a second here. What's T in 1995? T in 1995. 2000, T is 0. So what's T going to be? Negative 5. Can we do that? Yeah. In this particular model, we should be able to go back in time. So let's just put in negative 5 here. Negative 5 in our table. And it says we would have probably had only 180 deer if this model reflects previous time. And then it says, in what year will there be 1,100 deer? So again, this is a time that we're looking for. We want to find that time when we equal 1,100 deer. Now, remember, if I go to Zoom 6 here, this isn't going to show up anything because remember, this is negative 10 to 10, and it's pretty obvious that we at least need to go up to 1,100 to see this. So let's go back to our table so we can look at what possible values here. And I do have some numbers already in there that do help. You'll see we know at year 10 we were at 833. I already had 15 and 20 in here, and both of those are definitely larger than the 1,100. So depending on how big we want to see the graph, we could go to 15 and we're probably okay. So let's go back to our window, and if we want to go back in time, that's fine, but I do know that my X-max needs to change. I'll just jump to 50 years ahead. And then the same thing down here. I could change the Y-min, but I'm not. And then we do at least know we want to see 1,100. I'll just jump a lot higher above that, and let's just go to 2,000 and enter that. So again, my X is going all the way up to 50. My Y is going up to 2,000. Just to give us a good view of this, press enter, and there it is. Oops. And you can see I've got a little junk over here. And why would I see the junk? Because I didn't go up here and turn off my plots. You'll see that this plot is still on. So I could turn it off if I wanted to, and I will. Now my graph doesn't have that little extra down there. All right, oops, forgot to do something too. Remember, we're looking for our y equals 1,100, so we'll put that in our y2. And now we'll second and calc. Our intersection is option 5. It starts out with the blue one. I say yep. Then it goes to the red one. I say yep. And I'm not going to guess, and it's going to jump right here, and it's going to tell us what our t value is. It says that t equals, or actually it says x, but we know that's t, 12.718. Okay. Which means in what year? Of course, it's not the year 12.718. It would be sometime in the year 2012 that we reach 1,100 deer. Okay? And then here's a fun one to consider, and that's this. It says, hey, slow down here a little bit. What if it were linear instead? Who said it was exponential? Well, if it were linear, we're still going to use those same two values. Remember, we had 0, 300, and we had 5, 500. This is nice because if we're writing it in the y equals mx plus b, we know what our b value is from this directly, that b is going to have to equal 300. All we need to do is calculate our slope. So let's calculate the slope. We know the slope will be y2, 500, minus y1, 300, divided by x2, 5, minus 0. That, of course, will be 200. 200 divided by 5 should give us 40. We have a slope of 40, excuse me. So the equation would be y equals 40x plus 300. And it says, let's take a look at these. So let's just go back here to our y equals and get rid of that 1,100. And let's just type in this equation, 40x plus 300. And just take a look at them. Go to look at our graph. And boom. Okay. Hopefully you can see that the exponential growth really crushes it here, but in this time frame here, they're pretty close to each other. Okay? If you're looking at only this data, you might assume that the growth rate is linear. But over time, the exponential is going to overtake it. As a matter of fact, if we were to zoom in on this a little bit, I'm going to change my x max to 30 and my y max, let's just jump down here to 500. I think that'll work. And graph that. Oops, didn't get it. So, here. Sorry about that. And yeah, you can see that I didn't do that good of a job of setting up our x here. I probably should have gone down a little bit. We'll go to 15 and graph it. And now you can see that, yeah, that linear graph is actually above it for a little while, and then it gets taken over. Okay? So hopefully that made enough sense for you. What's that? Yep.
Is the homework online? Do you have a paper for it?
I think we've got a paper for you. Looks like fun. Oh, you're good. All right. I think we're good. We'll do the other one, the isotope one, later. All right. I think we're good.